Message on the front page, it's like, hey,
Yeah.
Yeah.
It's really nice.
February was so long. And then March is gone.
Yeah.
What happened?
February was the longest one that exists in March or something. Yeah.
Okay, so we are ready to start. So just a reminder that I have on my schedule on next class is going to be the Ceramic Spotlight. Is that right, Josh? You guys are still planning on that?
Yes.
Good. So next class, Ceramic Spotlight. If you didn't do it last time, you'll be doing it this time. And then we've assigned the 1800 class. They brainstormed ideas for ceramics. Some of them are going to be real bad. Some of them might be good. I didn't look closely at the list. In general, it was a mix from years past, is my observation. So you've been assigned these things. I think you can actually pick from that topic. Josh, correct me if I'm saying something wrong.
Yeah, they should have all picked it by last Friday.
Okay.
If they didn't, I signed up.
And I know Josh laid out a document that describes this. So basically what we're looking for, though, is for you to take these and imagine that you're the engineer working on the team at a company, and somebody on the team suggests, let's use ceramic for whatever, right? It's your job as the expert. The team's going to look to you, and they're going to say, can we do that? And Jared, and like, I'll still get Ashley, Megan, will say, like, here's the reasons why you can or can't. And then if it's a really bad idea, you're going to say, here's the reasons why this is not an appropriate application. And then you're going to suggest an alternative ceramic if that's possible. If it is a useful idea, you're going to say, here's how you go about doing it. Here's the processing step. Here's things to be aware of, right? You're going to provide the voice of like expertise on that topic, right? And this will happen to you guys, right? Whether or not ceramics as material scientists, when you go and work on teams, you'll almost always be on teams, they're going to have some idea that's going to have a materials problem. They're going to say, Mitch, can we use that? Can we use aluminum here? And you're going to say, well, and you'll give them your best argument for why you should or shouldn't, right? So this is a chance for you guys to sort of fill that role. Okay, there's that. We're pretty much on track, actually. Today we'll finish up chapter 14 and actually start on machining, so we might be a little bit ahead, which is good. And then a reminder that tonight, if you want to get some extra credit, attend the Bench to Bedside. It's at the Utah State Capitol. If you haven't been up there, it's pretty rad. Yeah, Bear?
if I get like someone to do David or do something like that, I like actually cannot be there.
If you cannot be there, then talk to somebody who did go there and write me up a thing. That'll work. But I'd like you guys to go. In fact, the Shira ladies are going to be taking selfies with you guys, they said, if you show up and go see them at their booth.
I really wanted to be there to support them, but
They'd be pretty rad. It's $5,000 up for grab if we get enough votes for them. So to get your extra credit, you do not have to vote for them. But if you want to go, I think it'd be pretty rad to support them. Yeah, Jake?
What was the time that was at again?
It goes from 6 to 9. In years past, up in the last 3 years, and they've got great food, and you can stay and come and go as long as you want. It's just like a big mingling. I saw like random local celebrities. I think the governor was there. Dieter Uchtdorf was there, if you know who that guy is. So it's a random smattering of interesting people there, and it's worth going to. And really cool projects, right? Okay, anything else? That's it. So let's dive in for today. Last thing we left off talking about last time, we did the boring part of sintering. Then we started talking about sort of the pragmatic part of sintering. We're going to wrap that up, and then we'll move to, all right, once you've made this thing and you've densified it, what needs to happen before it's ready for use, right? So we talked about overpressure sintering, and I'll remind you that the idea behind overpressure sintering was Le Chatelier's principle. The Chatelier's principle meaning if you've got products going to reactants going to products, and you just pack the house with lots of products, then you make it less likely for them to form, right? So if you want to sinter silicon nitride, but you don't want to form silicon gas and nitrogen, or silicon liquid nitrogen gas, then you just put this chamber with as high a partial pressure of nitrogen, right, initially, and it will prevent this from happening at quite as low of a temperature. It'll move to higher and higher temperatures. And this can be really good if you want to prevent it from happening. By the way, silicon nitride actually does decompose pretty readily, right? At high temperatures, it will decompose this way, and at lower temperatures, it's susceptible to interacting with water and air. All right, if you take silicon nitride and you put it in like a little Tupperware with air, in that air, even in Utah where we're very dry, it's got a little bit of moisture in the air. It reacts with it, forms ammonia. It's reacting with it, right? And so when you open it, you'll smell it. It'll smell like ammonia, and you're actually like decomposing your silicon nitride over time. So if you want to store them for whatever application, if you don't want it to break down at all, then you want to store it outside of the presence of the water, right? So you put it in a dry glove box. seal it, and you'll be able to use it just fine. Right? Okay, let's move to hot pressing. We've described lots of different shape forming processes and sintering. Hot pressing is sort of a mixture, though, of both shape forming and sintering, right? You do them both together simultaneously, ideally, right? So it's just like regular sintering in that heat, time and temperature are working. But now, in addition to time and temperature, you're providing a way larger force than just capillary forces, right? The pressure that you're adding to it can greatly enhance the densification effect, right? It improves particle packing because once you heat things up, you're applying this pressure so they're going to be able to pack together better. It also gives better contact between particles. If particles are touching firmly with one another, then the diffusion or whatever the transport mechanism is going to work better. And you typically get like a 20x energy advantage compared to pressureless sintering. What do we mean 20 times better in terms of energy? Well, if you fire something and you have to take it up to 1500 degrees and leave it there for 10 hours, think of all the energy that's going to go into that. That's a pretty enormous amount of energy probably. It depends on the size of your furnace and all that, right? Meanwhile, if you use a hot press, you're heating up that whole chamber, but because you're applying this load on it, you don't have to hold it for 15 hours probably. In fact, you can hold it for a couple minutes. So you can get way, way less energy consumption with these. So it's actually pretty advantageous if you're talking about reducing energy in production, which is pretty enormous. Like the power bill for some of these companies is pretty non-trivial. It's a pretty enormous amount of energy, right? So here's some advantages. You reduce your densification time because once you get it to the point where it's sort of softening and you got transport, by adding that extra pressure, your transport mechanisms just really take off. You can reduce temperature. Any thoughts on why you'd be able to reduce temperature? What's that? Sure, right? Temperature is basically saying it's giving you time and temperature. So you could do it for longer times, but at this lower temperature, or you go to higher temperatures for shorter times, right? You get smaller grain size because you're holding it for less time. We know the Oswald ripening, that's the process whereby small grains get swallowed up and turned into larger grains. That's a time-dependent process, right? Obviously, the more higher the temperature, the faster it'll go, but the longer you leave it there, the more it's going to coarsen. And if you cut down time, which we know we can by doing this, then your likelihood of having small grains is better. It's a better way to make small grain ceramics, right? You'll certainly get less porosity because you'll be pressing on it, right? And if you get less porosity, then you're going to have higher strength, right? You can remove adding sintering aids. Remember, what were sintering aids? Somebody remind me. What was an example of a sintering aid? Yeah, anybody remember this? Like MgO and alumina. What did MgO do in alumina? That one slowed grain boundary motion. That was one example. What were other things?
Something that melts and fills.
Yeah, a liquid phase sintering aid, right? That's another one. So it could be something that slows down grain boundary motion. It could be something that melts. It's something that's making sintering work better, though. And if you can just apply a force and get it to densify without that, then you don't have to worry about the downsides of having that. It's a leftover dopant. Maybe that's going to mess with your electronic or optical properties. It won't be totally transparent, maybe. Or maybe it's going to be a glass at your grain boundaries, and then it's going to have poor creep resistance, right? So you can get rid of that. And you can get rid of binder and organics, right? Because it's a shape forming and sintering process all in one. So you don't have to add binder to give it green strength because you're never going to take it out of the die, right? So you can greatly reduce your porosity coming from binder and organics, right? So these are all really good advantages, right? Is there a downside? Do you think of a downside to hot pressing?
Limited on shape.
Shape, yeah, that's going to be the big one, right? Because it's a uniaxial press essentially, right? And so what sort of shapes can you achieve? Constant cross-section. Pretty simple shapes, for better or worse, right? It works for some things, it's not great for others. Are there downsides to this? Are there other downsides? Anybody used a hot press before? Yeah, Barrett? Tell us about it. What's the process like?
Like in manufacturing sense, it's kind of slow.
It's way slow, right? Because you're going to put one sample in there. Maybe there exist dyes where you can do multiple samples within the same set of dyes. I don't think so. More for the vast majority of compounds, you're going to be making one sample at a time. This thing has to get heated up to, since you're sintering at the same time, it's pretty high temperatures. Then it's got to cool down. It's a really slow process, right? So this is not fast at all. It makes sense if you're pressing maybe billets. What's a billet? It's like a long rectangular shape or something like that you're then going to cut into smaller pieces and do something with, because then you can get many samples out of one. But if you're making like one individual piece every time, that's going to be a really energy expensive, costly, slow batch process, right? So it's not ideal in terms of, it's certainly not a continuous process. But it has all the advantages that we listed, right? Other advantages, disadvantages you haven't thought of with this? Okay, how about this? How are you going to apply the pressure during sintering? How do you take a furnace and apply a pressure to it? We kind of talked about this the other day, I think. How are you going to apply a pressure? You could take the furnace in the 2010 lab, little box furnace, right? And while that's running, you take a pair of pliers and squeeze on your thing, right? That's one option. Tell me what's wrong with that option. What are the downsides to that option?
You have to open the doors.
You got to open the door, so your temperature is going to be, first off, crazy. It's not going to be a constant, homogeneous temperature. What else? It's going to be using a lot more power because you got the door open, so you're losing energy.
Non-uniform pressure.
Non-uniform pressure. Yeah, if you took your pliers right onto like a little pellet, that's going to be non-uniform. If you took like a little vise and you twisted it down inside there, instead of a die inside there, it'd be a little bit better. But still, if you put a pliers or a vise in there, what downside is there to putting that in a hot furnace? What's that? Yeah, what if it melts? Ceramics were by their nature, they're generally very high melting point things. They sinter at very high temperatures. If the metal doesn't melt, it's certainly probably going to be corroding, right? And that certainly happens. Like my student Layla, she's making a series of measurements where she has to take and clamp these samples together. And the way that she's doing that is mechanically. There's these long threaded screws, and she puts nuts down on these ends, and they just sort of clamp down. And they work a few times, but these things corrode so much that she only gets like 3 or 4 uses out of them, and then she's got to switch them out. Right? So just because metals in an oxidizing atmosphere, generally speaking, are going to get corroded pretty bad. So how do we fix those problems? If we're not going to do that, because we don't want to constantly be replacing these things, how would you design this furnace? What do we got to get rid of?
The furnace.
The furnace. Yeah, that's like what they did with SPS. They ditched the heating elements altogether. They heat your sample directly by passing current through it. What else? So it's really the oxygen, right? It's the oxygen that's there that's causing the problems, right? So for a hot pressing furnace, generally speaking, these are done not in air. You evacuate the air out, and you backfill it maybe with argon, or just leave it under vacuum, right? And then you heat it up, right? So now that there's no oxygen present, the steel that this thing's made of, or whatever it is made of, is not going to get corroded, right? What would this device actually look like? So now you've got a furnace. It looks like a box furnace, but you have, somehow you're going to apply pressures, right? So you have to have probably openings on the top and bottom where you can have platens. Platens are like punches that can move up and down, just like you're doing axle press, that they can go through while keeping, so they have to be able to move. We have to keep air out, so that you have to have this airtight seal that allows mechanical motion. That sounds a little tricky, right? What materials can you use? Again, if you're going, whatever, it has to withstand the high temperatures you're going to. So oftentimes they'll use refractory materials in there, right? Or just limit the temperature it can go to. Like they'll use graphite as a really good material. Graphite, there's no oxygen present. Graphite can go to like over 2,000 degrees, right? What limitations? We talked about that. So let's skip this. All right, so hot press properties, you can get near theoretical density using these things because, again, you're at such high temperatures and you're applying force, you get close to theoretical density. Less grain size, no sintering aid, better high temperature crete because you don't use sintering aid, stress rupture. Another thing that happens, though, is you get orientation. Orientation, if you guys remember, I think we've talked about this semester. Orientation is what again? Preferred orientation or texturing. What does that mean? What's that referring to?
Things go the way they want to.
Yeah. Imagine that you've got a crystal structure like this, right? You've got grains that are like that, right? Maybe it's like a layered structure, so you've got layers like that. If you have a bunch of these different grains that initially crystallized, maybe you made them via co-precipitation or something, so you've got little nano particles of these things. When you press on them, what's going to happen to these things in a press? Yeah, they're going to line up, right? These things, if you pressed on like a bunch of straw, the straw is going to lay flat, right? Some of it might sort of stand up, but not very many. Most of it's going to lay flat. That's exactly what happens in hot pressing, is that you get alignment in one dimension, right? So you had a bunch of these little needles. They were all random. When you press it, they all lay flat, but they're not all lined up the exact same way flat. They're going to be like, they have 360 degrees orientation here, right? So if you measure with X-ray, what are you going to see? If you look down on it this way, what will you see? Yeah, you'll see, do I have a picture of this? I know I have at some point. Basics of X-ray, maybe I've got it, no. Well, I don't remember where I've got it. But you're gonna see, let's say that you've got a bunch of peaks that are possible in your sample. You're gonna see only some of them showing up, right? If, for example, you normally expect as a function of 2 theta to see peaks here, 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 and maybe this is like the 100, the 110, the 111, you know, whatever it is, right? If you've aligned your sample, you won't see all those peaks. You might only see like that one, and it's going to be really big, right? So you're going to see 001 style samples because you've aligned it to your C-axis, right? So anything with a C-axis indicator in it, you're going to see those really strongly, and these ones are going to get really reduced, right? Okay, so that's a way that you can test for texturing. In fact, from these values, you can calculate the degree of texturing or the degree of orientation that you've achieved. Yeah, Chris?
I'm curious, why is reduced grain size a good thing?
But not necessarily a good thing. It just depends on the application. Can we think of applications where small grain size is desirable? Yeah, fair. Yeah, not higher density, but smaller grain size. This is like one of the key concepts you learn in Intro to Material Science. It's called the Hall-Petch equation. Basically, the smaller the grain size, the more grain boundaries there are. Why should that strengthen a material?
Dislocations are harder than dislocations.
Dislocations get blocked by them, right? So again, yeah, we don't usually think about grain dislocations moving through a ceramic as well. So why would they be desirable for ceramic? Strength is a little bit better in these. Yeah. Other ideas? So why would we want small grain size? Yeah, Josh?
Some applications that are small enough, they won't scatter any light.
Yeah, a couple of classes ago we talked about that, right? We said that the Rayleigh scattering is when light has a certain wavelength, 200 nanometers or so. If you've got your grain size way smaller than that, then it doesn't get scattered by it, right? So if you want transparent ceramics, you want to get all the porosity out, obviously, but you also want small grains. Alumina, you can get alumina almost 100% dense, and it still looks white like this board, right? But if you get that grain size small and get it dense, it's transparent, right? Which is great. Other things? Why might we care about small grain ceramics? Well, smaller grains means more grain boundaries. Could that be advantageous for anything? Cracks will certainly interact differently with a grain boundary than with the bulk. That could be positive or negative, just depending on the system. Diffusion, the same way. You can, generally speaking, have much higher diffusion along the grain boundaries. That could be desirable for something. So, generally speaking, smaller grains are oftentimes desired, but that could not be the case. Okay, so we've talked about the fact that this is going to orient your samples, and you see that really quite a bit, right? So, for example, here, like they'll call this sinter forging, which is when you achieve this orientation as you're sintering it under a press, so under a forge, right? So silicon carbide whiskers that initially had like a 20-to-1 length to diameter ratio, so they were like these long little rods of silicon carbide. They had strength over 600 megapascals, perpendicular to the hot pressing direction, and only 400 megapascals parallel to that direction. Because basically we know that properties that have anisotropic crystal structures, meaning they're different directions, end up with properties that depend on the direction. So you can use this to your advantage. What if you have an application where you can only use it where it's perpendicular to that hot pressing direction? You're going to benefit from a higher strength, right? So this texturing doesn't have to be a bad thing. It can actually be a really good thing. For one of the things that my student's working on, she's making these beta alumina. Beta alumina, if you remember back a few chapters ago, that's the sodium ion conducting ceramic that is a very good material for that. Well, again, the sodium ion conduction happens along these layers, and if you make all these things lay flat, now you've got really good sodium ion conduction through that layer, right? Better than if it was just randomly oriented. So that's an example where we're taking advantage of texturing. But the limitations, as Chris mentioned earlier, is the shape. Hot pressing is not great for making different shapes, right? if a component has a non-uniform cross-section thickness, then different parts of it will have to compact at different ratios, right? So imagine trying to press this thing, and the book has a picture of it. But let's imagine you're trying to press this shape, right? That's your final product. That's looking along the side of it. You want to make this thing. If you try and press that, imagine what has to happen. You have to have this stuff compressing not very much, but this has to compress like a whole bunch, right? But you're really just going to put like a punch on this thing and press on it all. So when you start pressing on it, you're going to run into a problem, right? First off, this isn't going to see any pressure at first, and this is never going to compress to the point where you do get pressure on here. See the problem? So the book gives a clever idea on how to fix this. Anybody read ahead and see this? I don't know how commonly it's used, but it's a clever idea. They take this, which is the powder that you want to make, right? And they put it in a media of something like sand, something that can flow a little bit and transmit the pressure uniformly. So if you start pressing on this, all that sand, it starts to look kind of like an isostatic condition, right? And even better, as it starts to compress, this sand can flow a little bit. And so ideally, it should be able to cause this thing to compress kind of like you want. And then even better, they use different dyes. They use a dye that looks like this. Right? They'll use a dye that is exaggerated like that. So again, they're hoping that they can transmit different pressures to different parts of it by changing the dye shape. I've never used one of these. Again, you have to hope that the powder is going to redistribute evenly during pressing. Otherwise, parts of it's going to be denser than others, and therefore you get cracking and the problems associated with gradients. Right? So they'll call this pseudo-isostatic approach or non-rigid tooling via powder bed. Like I said, I've never tried this. I just know that it's a possibility. Okay, we've said probably enough about SPS. I'll only add one more thing here. SPS, this is one where you pass the current right through your sample. There is a lot of debate in the literature about what's going on here because you pass just a huge flow of electrons right through your sample. So there's a question is this flow of electrons changing the transport properties? Is there something called electromigration, right? Where your ions that normally hop through material, and we know how they do it as a function of time and temperature, is that changing when there's this giant like river of electrons flowing through the material, right? Some people think it's a very big deal and that it is changing things, others don't think so. I think the jury's kind of still out, but doesn't seem to be a ton of evidence that it's playing a big role, and other people would disagree with that statement, but that's what I've observed, right? And again, there's no spark, there's no plasma. That was when they first made it. It was like, I think they were just like shorting it out. They saw sparks in there and thought, oh, maybe these sparks are cleaning the surface of the particles, and that's giving better contact. Or, they had some ideas early on. I don't know if any of those have really been borne out. But the name stuck, right? People have tried to change the name. They'll call it pulsed electrical current sintering, PEX, or they'll call it current assisted densification, CAD-Pro. SPS is only stuck, though. How about this? How are you going to know when sintering's done? Whether it's hot pressing or SPS, how do you know when you're done? Any ideas?
Guess.
Take a guess. Just try a few. What do you think, Barrett?
Can we just order it?
Yeah, so both of those options are like, do it, take it down, take a look at it, right? Is it the same color? Measure the density. Is the density close to theoretical density, right? How could you do it in situ? In situ means while it's happening, inside of its sort of device. How could you determine whether it's done? Well, think what levers you have and what knobs you have that sort of control what things you're observing in this compound. Observing it's going to be hard. It's inside of a die, so you're not going to actually look at it, probably. What do you know about it, or what's happening?
It's volume.
Yeah, that you're on the right track. How do you know it's volume?
By where the die's at.
Yeah, so these top and bottom punches, you do monitor those really carefully, right? You know the crosshead location on this instron at any given time. In fact, you're applying a load on it and you're watching that crosshead change. So what's the crosshead going to do when it's done sintering?
Stop moving.
It's going to stop going down, and if you keep heating it up, what should it actually do?
Go back up.
Why would it go back up? A good guess. Yeah?
So as a guess, but I assume it's absorbing heat to cause the parts to those bulbs to get the metal start actually increasing the temperature.
So then you guys are right there. Thermal expansion.
Yeah.
Yeah, so this is the sort of curve that you can look for. It looks like this. If you were to plot, let's say like the crosshead location, how do we call it? Let's just call that the y, right? That's the distance that this crosshead's moving down in the y as a function of time. This would be all at the same temperature, right? We're holding at the same temperature, we're applying the same load. You're going to see that this initially, it's going to drop like crazy at first as the particles rearrange themselves. And then it might start to sinter, but then it's going to go up slightly. When it starts to go up, you know that sintering is done, and it's still just getting warmer and warmer, so it's actually starting to expand. So you're done at that point. And this is really easy to monitor, right? Most of these things are built on an Instron frame, and you can monitor that crosshead displacement in real time, and it doesn't take very long. Because you're doing this at high temperatures and you're applying the load, 5 minutes is a typical hold time, right, for these things. So really, really fast. And then when you see it starting to go up, kill the power. You may maybe not just want to kill the power directly because then you might thermally shock it. So sometimes they slowly cool it down. How do they cool these things? How would you guys cool it? Or a hot press. They look very similar. It's hard to see in this picture. There's these clear tubes running. Those actually have water running. And they run, you can see right along that sort of that line. On the top of that giant chamber, they've got this sort of serpentine pathway where water can run along the outside, so the whole chamber is cooled. And then how do you cool the sample? You actually have water running down through this platinum and then back out, up through this platinum and then back out. So the punches are actually water cooled themselves. And by doing that, you can cause this thing to cool down pretty quick. And it still is the slowest part of this process. Like I said, sintering takes 5 minutes. Cool down is the slowest part of the whole thing. It takes about an hour, maybe 2 hours. Right?
So
Probably
if you
just
just
faster, but
If you just expose it to air, that'd cook too fast.
it's a graphite dye inside of here, and so just your sample's heated up, but your sample might be heated up to 1300 C, where it's radiating quite a bit out. If you were to expose oxygen in there, that radiative heat has the inside edge of the steel quite hot. It would start to corrode, and other things might start to corrode. Your electronics, your thermocouples might be air sensitive. So generally speaking, you don't open this until you're around 200 degrees Celsius. There might be other systems out there that are more robust. That's the ones I've used, is you let it cool down on its own until it's around 200. And, the outside actually cools off really quickly because it's only being affected by radiative heating. It's the one that takes a while to cool down is your sample, the dye itself, and that takes, an hour, maybe 2 hours. And that's the slowest part of the process. But monitoring the crosshead is... people don't realize that a lot in the industry. Like a lot of people just throw it in, they follow a recipe, they're not actually watching, and then they over-sinter it. They cook it for longer than it needs to, and grains grow larger than they want them to in many instances. Okay, there's something called hot isostatic pressing. This is a really cool technique. It's similar in principle to cold isostatic pressing. How do we do cold isostatic pressing?
Dry bag or wet bag.
Dry bag or wet bag. If it's wet bag, you put your sample inside of a water impermeable but flexible membrane, right? Like a neoprene bag or something. You put that whole thing underwater, you pressurize the water, right? That's cold isostatic pressing. Hot isostatic pressing is pretty rad. You can do it up to about 2,000 degrees Celsius. So no water is going to survive that, right? So you're clearly not using water. Instead of using water as the pressure medium, you're using a gas, right? So you put it in a box, an empty box, you pump this thing full of some gas, and then you apply pressure to that gas itself, right? They'll use helium or argon because they typically don't want it to react with your sample. And you can go up to just bonkers, right? 45 KSI, 45,000 KSI, that's an enormous pressure, right? So you can apply crazy pressures at crazy high temperatures. This is the gold standard, best way to densify ceramics, right? How are you going to achieve it, though? Think about it. You're using gas to press on your sample, right? You're not putting it in a bag like before, right? What bag would you use? Nothing's going to survive 2,000 degrees Celsius, right? Well, no polymer is, but a ceramic would. So what they do is they seal it with glass frit. So you pre-consolidate your sample. So you have to do the shape forming process using any of the techniques that we used previously, right? You make the shape kind of look like you want it to, and then you have to paint on a glass frit, right? That glass frit, when you heat it up, is going to form a gas impermeable separation. Why do you need that? Why has it got to be gas impermeable? Barrett? Not steep, but go into it, right? Yeah, basically you want your sample to look like this, right? You've got like the ceramic that you want to sinter, and it's got pores and whatever, right? That you're going to try and densify. You have to put around it this gas impermeable layer such that if you have a really high pressure here, you still just have pressure at atmosphere inside of here, right? So you have a pressure differential. That's what causes the isostatic pressure on this thing. If this was permeable, then your helium gas would go inside of here, and you've got the same pressure on both sides. It's not going to actually make it smaller, right? So it's got to be gas impermeable. That's the hardest part of this process. This is the best process set out there for getting the densest, strongest, all the way dense samples, but it's going to be a slow process, right? It's not going to be fast like SPS where you can achieve nanostructures, and you have to put this gas impermeable layer on it, which is kind of tricky because then you have to get rid of it probably when you're done. But this is definitely the best way to get the densest samples possible. Barrett?
So why does it look like glass layer, but
Why doesn't it break?
yeah, because it's squeezing this, right?
That's a good question. So it's at higher temperatures than the glass. It's not in its glassy regime. It's way above its glassy transition temperature. So the glass, I don't know if it's a thin molten layer or what it is, but it's not brittle for sure. That's a good question. I don't know exactly what's happening in that material. I know that it's glass that they use, but you're way above its melting point. So I don't know if it's like a thin liquid or what it is, and how it stays impermeable. It's a great question. Yeah. Or did you have a comment, Josh? Do you know the answer?
No, so the 45,000 KSI is like 313 gigapascal. You want to put that in?
313 gigapascals? That is bananas. Like, that is absolutely bonkers. Huge, huge, huge pressures you can achieve. So if you guys worked with Shetty, is anybody doing a senior project with Shetty this coming year? He does hipping a lot of his samples because he wants to get them just fully dense. He's making drill bits and stuff. And this is the way to do it. Did you have a question, Jared?
Yeah, how's this at complex shapes? Because it seems like all that pressure would just turn any complex shape into a ball.
Well, it's isostatic, right? And so, yeah, like let's say you've got a shape that is complex, that you've got like a C shape, right? Well, you've got pressure pressing here, right? It's just isostatic, just like you can, yeah. So it's an interesting combination of the different techniques we've talked about. It's net shaping, but it's really high temperature and really long. You still have to get rid of that glass layer. These are all just trade-offs you have, right? I'll say this is extremely expensive. We don't have one here. I don't think Ceramotech doesn't have one either. There is a company that'll do it for you, and you send them your samples. They'll hip it for you. Okay. That's all I'll say about that. There's also chemical sintering routes. So in these ones, you compact a powder into the shape that you want. You can make something that looks like a turbine engine, for example, right? You heat it and react it to form powder. If it's combustion synthesis, the exothermic of the reaction itself causes sintering, right? So this is something where as it starts to sinter, that's giving off a lot of heat, and that self-propagates the reaction. That was popular for a while. But the solid powders that this compact is made of, they can also react with liquid or gas that you flow into the chamber, right? And I think the book gives an example of silicon carbide where they start out with, what do they start out with? Do I have this here? Oh, that's here. Okay, yeah, right. So you start out with silicon carbide and carbon, and you shape that, and then you expose it to molten silicon, right? So you want to make silicon carbide eventually. So by starting out with silicon carbide and a little bit of carbon, you don't have enough silicon, right? You want to add some silicon to make this thing turn into full silicon carbide. Well, what's great is these are both solids, but then you expose that additional silicon that you want in the form of a liquid, so it flows into it, and you not only satisfy the stoichiometry, like you're going to get enough silicon to have pure silicon carbide all the way through, but it fills in the voids as it does so. So it's a nice process for that. Of course, you're relying on diffusion for that silicon to spread itself and react with all of the carbon. That might be easier said than done, right? And if you don't have the right amount, you're going to end up with a composite, maybe excess silicon and silicon carbide, or excess carbon and silicon carbide. You might end up with a composite instead of just a pure ceramic material. There's chemical vapor deposition. So imagine this case, you've got silicon powder, you make the shape first, looks like a turbine engine blade or something, or whatever you're making, right? You fire it in nitrogen overpressure. Now, because it's an overpressure of nitrogen, you're going to want to go from products towards reactants. So you're going to form silicon nitride, right? We normally think of silicon nitride decomposing at these temperatures, but because you have a constant overpressure, it's actually going to form silicon nitride, right? And so everywhere that you had these interstitial sites between the silicon particles, that's going to get filled in as these things slowly grow. Is there a downside to this? Yeah, what's the downside to that? That sounds really great, right? Make a compact of silicon, just heat it in nitrogen, voila, you've got silicon nitride. What can go wrong there? Any ideas? Get there?
You did it for you have to be
Yeah, what if there's some oxygen left over? Then you're going to form silica. That might be not what you're looking for. Let's assume we even get it all out, though. The problem that they run into with this is that, okay, you've got a bunch of little particles in your ceramic, right? And you're starting to introduce nitrogen gas, and you're hoping that it's going to then form a new particle of silicon nitride. What can happen is you can form it, you will form it most rapidly at the surface. That's where it's in contact. It can actually form a gas impermeable layer of silicon nitride and then block off the stuff inside. So you might end up with a graded material where you have silicon nitride at the edge, but once it blocked itself off to further nitrogen gas, you're done. And that could be pores left over on the inside. It certainly be unreacted silicon. It's not a very good scenario. How would you prevent that from happening? What things would you maximize and minimize? Yeah, what do you think?
maximize dispersion.
What's dispersion?
So making sure that your particles are far enough away that they won't form that gas.
Okay, so let's say you start with like a nice uniform particle size, all the same size. You pack it. Its density of packing is pretty uniform all the way through. Is that the best we can do? Or is there anything else we can control? Ryan, what would you do? Oh, okay, yeah, that's a good idea. So while you're passing gas through it, yeah, if the sample's heated, maybe you could get some diffusion of your nitrogen into your sample to keep on reacting. That's one good idea. What else can we do? Yes, that's what you do. And the key is to go slow. If you just like douse this chamber with nitrogen, then you're gonna have food reacting really quickly, right? But if you just pack it with a lot of inert material like argon and then a little bit of nitrogen, then it's gonna be able to travel all the way through it. And so you're gonna slow it down so gas is able to travel all the way in and all sort of fill in at the same rate. That can help this process, okay? It's still an issue though. I think it's hard to get these things fully dense. I imagine they follow that with like a hipping process to try and get the rest of the density, right? Okay, there's cementitious bonding. This is like cement, right? Like concrete. You make concrete, you're adding gravel and rocks and sand and stuff to something that's going to be able to bond cementitiously. You add water to it, let it sit, it gets hot, a couple days later it's bound up, right? That's cementitious. So it can be, there's different types, there's hydraulic, there's reaction, there's precipitation. Portland cement is an example of hydraulic reaction, it's probably the most common one. You start out with anhydrous calcium silicate, that's what cement is, right? When you add a little bit of water, it forms the hydrated version as opposed to the anhydrous, meaning no water, it forms the hydrated version, right? This is exothermic. If you ever, anybody cast cement before? It gets super hot, right? It gets really, really hot. And that can actually dry the material out. Parts of it might dry out way faster than other parts, and then if it's dried out and the parts of it near it aren't, then you get the same issues with like, it could be thermal expansion, it could be just drying, but you're gonna get stress gradients and cracking. So you actually have to keep the surface damp. If you've ever done this, they'll have you like maintain the surface damp a little bit to prevent that from happening. And then you want as little water as possible if you're trying to make a really strong ceramic, because if you have excess, it'll lead to porosity. Porosity leads to low strength, right? But if you don't have enough water in these things, it won't be workable and it won't maybe flow very well, and you might have a big pore just because it didn't flow well. So it's a balance between flowability and workability and porosity left over by excess water, right? Yeah, we don't maybe think about ceramic, Portland cement as a ceramic, but when you process, it's just like an injection molding in a lot of ways. You're like trying to shoot it into some sort of cavity, and you're hoping that it won't have nit lines or voids, but just like any injection molding process can if you have controlled viscosity. And then obviously you can add all sorts of things to ceramics, like cement. When you add things to cement, it becomes a concrete. You can add rebar, like reinforced cement, right? You can add gravel. You can add things that you're going to burn out later on. If you've heard of pervious concrete, this is pretty cool. Anybody use pervious concrete for anything? Pervious is pervious to water, so they make these channels in it. Pull it up real quick. Internet, maybe. Got no internet. Pervious concrete is you add something to it. That you intentionally know will leave behind holes so water can flow right through it. Why would you want this?
So that you don't get water issues.
Yeah, like the first house I ever lived in, I had a driveway that pointed down towards the garage. Worst thing ever. It flooded like all the time. We live in Utah. It didn't rain that much, right? It flooded all the time. If our driveway had been made of pervious concrete, that water might have been able to flow down to a gravel bed below and not go straight into the garage. And they're pretty impressive. Water will go like right through these things. So how would you actually achieve this? How would you make this stuff? If you guys were the engineer at the company, you go get a job at Staker Parson, and they're making their new pervious, concrete. What would you tell them to do? Based off the things we've learned, how would you go about this? Okay, so you go the route of trying to burn something off. That's one option. There's a better way. That would work though. Barrett, what would you do?
Farm particles that.
Yep. Do you want them to be the exact same shape, size? What do you want?
Yeah. You want them to be similar in size so that you don't have small ones that make one.
Similar size but different shape. We know that different shape leads to poor packing. And that's what you want. You want poor packing. You want regions of empty spaces and water can travel through. And then key here is you want way more aggregate, which is the thing you're adding to this, than you have cement. You don't need much cement. You just need a skin basically that causes these aggregates to bond together. But you don't want to totally fill it in. If you fill it in, you got concrete, which is impervious, right? You want pervious concrete. Yeah, right?
I would imagine that this would make it really weak.
Definitely. Definitely weaker.
So
Yeah.
would you even be able to, like, in the driveway example, would you be able to hold your pod?
I don't know if they make roads out of this and stuff. I think that they do. I'm not an expert though. They're more.
Yeah, they
In the parking lot, so?
This
This is a driveway. Or on walkway. Oh yeah, that's the idea though, right? This would fix a lot of the issue with runoff, right? It's a pretty cool technology that we don't see, so maybe it's got some limitations that are not obvious to me. But okay, 5 more minutes. Let's keep going. There's other though, so that's a hydraulic cement. There's also reaction bonding. This was my whole 2 years of an internship at Ceramic Tech was reaction bonded aluminum phosphate. You start out with alumina, you add phosphoric acid, it bonds to form AlPO4, right? And it gives off water as it does so, right? Because that hydrogen's got to go somewhere, and there's a little bit too much oxygen as well. So it gives off water, and it forms this aluminum phosphate ceramics. That's another way. Lots of those. There's precipitations. We've talked about those kind of already. There's something called pyrolysis, where you start with polymers, and your polymers are going to be mostly carbon, right? But they could have other stuff. They could have nitrogen or silicon, right? And then you burn these things, either with an electrical current or you just heat them up, but you do it in the absence of oxygen, right? So it's still going to degas quite a bit, but you're not going to consume all your carbon. It's not going to turn into carbon dioxide. Instead, it's going to turn into powders which might be of interest, right? So Dr. Cutler, do I have it here? No, I don't. His dad, though, yeah, I don't have this. His dad's famous for making silicon carbide. Dr. Cutler's dad founded our department, right? Like in the 50s or whatever it was. And he was famous for this. He took rice hulls, like the shell around rice, and he found out if you heat it, it's got pretty much the exact ratio you need of silicon to carbon to make very nice silicon carbide, right? So you heat it up in a pyrolysis type of situation, you get a bunch of what they called whiskers. Nowadays we'd call these nanomaterials because it's nano everything, right? But really, really small particles of silicon carbide. And so there's a lot of people exploring how do you make cool ceramics by doing pyrolysis. Is there any advantage to this? Or is it just wasteful, right? You're clearly going to burn off a lot of stuff. You're going to start with a commodity product and you're going to turn it into something else. Is it really better? Can you think of any advantages?
Well, if you're using rice husks, using your waste product.
That's a great one because it's waste. A lot of times they'll use actually pretty expensive starting materials. You're going to use some siloxane polymers, right? Because those have silicons and carbons, and that maybe is what you're looking for. Why do all that waste, right? You spent all the money to make the siloxane in the first place. Why are you using that? Can you think of an advantage out of this? That right there. Excellent way to make fibers. Why is this good for making fibers? Garrett?
Well, I was going to say fibers are typically very strong. They don't have very many flaws.
Oh, sure. We know why we want fibers. Oh, yeah, because their volume is small, so they have a low statistical odds of having that failure in them or flaw in them. Is it easy to make polymer fibers? Pretty darn easy. Compared to ceramics, definitely way easier. So what if you took a bunch of these long polymer fibers, laid them in your furnace, heat it, and now it's going to shrink, obviously, as you burn stuff off, but you're going to be left with a ceramic fiber. So that's the real advantage here, is that some shapes are really nasty to make as a ceramic, can be made pretty easily as a polymer, and then when you pyrolyze it, you can get a pretty interesting shape that would be really hard to make otherwise. You'd have to sort of extrude these things probably as a ceramic, and that may be a non-starter for them. They may not be very friendly to the extrusion process, so this is a nice way to make ceramic fibers. Right? There's melt processing. I'm going to skip that because we're taking longer than I thought. There's single crystal growth. Scarpula and myself in our department are going to teach a class on this, probably starting next year. Single crystal growth, there's lots of ways to do it. There's the Verneuil process, there's Czochralski method, there's heat exchange, the Skoll method. You should read through these in the book, they're pretty interesting. We care about single crystals because they tend to have better and better properties because you've gotten rid of grain boundaries. So in a lot of instances, you don't get any scattering if you want electrical transport to be really good. It's not going to get scattered at grain boundaries. But how do you make these things? So in the Verneuil process, you take a hydrogen torch, so H2O2 torch, and you spray in a little bit of like Al2O3 powder, just a little bit, really dilute in with the gas of it. That's going to melt it, hopefully. It's going to turn it into a very soluble phase, like a vapor phase, which will then condense onto some substrate and slowly grow, right? So this is like a vapor growth process, right? It's going to be really slow, right? But you can make synthetic gems, right? They're not going to be as real good in terms of their optical properties as like naturally formed gems, but pretty good, and they'll be the actual same material. The Czochralski method is a great method, though. There you actually melt everything. You touch it with a seed crystal, and you slowly draw that seed crystal out. So the hot zone is down here where everything's molten, and you're trusting that up above that it's not quite as hot, such that if you touch it and slowly draw it out, it shouldn't want to be molten. It should be a solid, so you can slowly draw that out. They usually spin it as it does it. And that's how they make these giant silicon wafers for the semiconductor processing industry. They melt the silicon, touch it with a single crystal, and they draw it out. And they can make really big wafers now, like 12, 16 inches, I'm sure. I know they can do 12. I think that they're actually maybe even above that now.
I think 12 is like about the limit because they're huge.
They weigh a ton because they
Yeah.
draw them like, I don't know, 10 feet long. I don't know how big they are. They're very big, but they can grow these things, right? That's the Czochralski method. You can also do something called edge-defined film fed, which is where you touch it with something that has a specific shape, like a tube. Like imagine you touched it with like a tube that has a single crystal on the edge of that. You touch that and then you draw that out. Now you would be drawing a tube, which is really nice because single crystals can be super brittle. They are super brittle. So if you could make a big block of it, but if you wanted to make a tube out of that, first off, it'd be crazy expensive because you're drilling through ceramic. That's always expensive. Drilling through a single crystal is going to be even more expensive because single crystal is so expensive. So this is just a better way to do it. You draw out the sort of net-shaped tube. Heat exchange, we already talked about, the group that did silicon carbide talked about that. Skull melting. Skull melting is pretty cool. You start out with a lump of powder, and you pass a current through it. And on the inside, it's going to be the hottest, and on the outside, you're sort of blowing air on it. And so it cools off and it solidifies. So that's what they call it a skull. Is the outside's a shell that's hard, and the inside's molten. And if you slowly then release the current, it should have a temperature gradient that causes it to slowly grow. If you do this right, you can grow big single crystals that way. So just some really cool ways to grow things. All right, we've got like one or two more things to talk about, and we'll do those next time, and then we'll jump to machining.